fundamental constant, which was the subject of my PhD I have done many years ago. So, as you probably know, our knowledge of the property of nature is based in two theories: general relativity, which describes the gravitational interactions, and the standard model of elementary particles, which describe the electromagnetic strong and weak interactions. So, all low energy phenomena can be very well described by the solution of the equations of both theories. However, in this picture there is something important missing, and this is namely that in these equations there are 20 parameters that are not predicted or determined by the theory. They have to be determined by an experiment. These parameters are the ones that we call the fundamental constant, and examples of them are the gauge coupling constants of the electromagnetic weak and strong interactions, Newton's constant, the masses of the elementary particles of the standard model. For this I put a chart just to remind you the particle content of the standard model, and also gyromagnetic factors of atoms. And in this talk, and as it's usually done in such research, I will not describe experiments or theories that I will not describe directly how the gauge coupling constants of these elementary interactions affect the different bounds, but I will talk about related constants that are more familiar to us, such as the fine structure constant, G of Fermi, that is related to alpha 2, the gauge coupling constant of the weak interaction, and lambda QCD, the energy scale of the strong interaction, which is related to alpha 3, the gauge coupling constant of the strong interaction. I will not be talking a lot about alpha 3 because it does not affect the bounds I am talking today, but I will be talking a lot about the fine structure constant alpha and some experiment also about G of Fermi. I will also not consider bounds on the gravitational constant, because you should have a seminary especially for this. And I will consider the variation of the electron mass, and also in this talk the proton mass will be considered a fundamental constant. The reason for this is thus that if the masses of the elementary particles, such as the quark, may vary with cosmological time, then the proton, which is constituted by quarks, the mass of the proton, will also be varying with time. So I forgot to tell that feel very free to interrupt me at any time, and also if you want to place some question in Portuguese, you can make it. I understand Portuguese not so well, but I will do an effort so it's more easy for you to ask any question you want. Okay. The first one who proposed that the fundamental constant may vary with time was Dirac in 1933. And he proposed this due that he noted a remarkable coincidence, namely that the quotient of the electromagnetic to the gravitational force between a proton and an electron is about 10 to the 39, while the quotient between the age of the universe and the time it takes for the light to pass through a nitrogen atom is about 3 orders of magnitude less. This remarkable coincidence made him to propose the large number hypothesis, according to which one or more fundamental constant may be simple functions of time. And in this slide, he proposed that G of Newton will be a function of the age of the universe to the -1. Following a different path of research, but in the same year, Milne also proposed that the gravitational constant should vary with cosmological time. Following Dirac's idea, in 1948, Teller proposed that the fine structure constant could also be a function of cosmological time, but this time as a logarithm function. This proposal was ruled out then by Pochoda and Schwarzschild in 1964 because they showed that this proposal cannot explain the observed luminosity of the sun. In an attempt to rescue Dirac's idea, Gamow, in 1967, proposed that while the gravitational constant should remain as a constant, the fine structure constant could vary with time, but this time as a linear function of time. However, this proposal was also very quickly ruled out, first by Dyson using the abundance of long-lived beta decayers in meteorites, and then by Bacall and Smith using quasar absorption system spectra. However, the interest in the time variation of fundamental constant got renewed with the development of granonification theories. These are theories that attempt to unify the four fundamental interactions. And more recently, phenomenological schemes were proposed just to model the variation of alpha, the electron mass, and the velocity of light. Without, these are phenomenological schemes which do not attempt to unify the four fundamental interactions. They are just proposals to see if this constant may vary with time. The different versions of the theories I mentioned have different predictions of the time and or space variation of the fundamental constant. And in this sense, the bounds from local and astronomical data are very important to test the validity of these theories. So the outline of my talk is as follows. The first part of my talk is devoted to bounds from local and astronomical data, and in this sense, first I will begin describing the bounds from the Oakland nuclear natural reactor that operated about 1,800 millions of years ago at the present site of the Oklo mine in Gabon, Africa. Then I will continue describing the present most stringent bounds we have today for the variation of the fundamental constant. They arise from the comparison of atomic clocks with different atomic numbers. Then I will move on describing the astronomical data. The most important method of astronomical data arrives from quasar absorption systems, and this method was the one that about 10 or 20 years ago there was a claimed variation about a claimed detection about the variation of the fine structure constant. I will discuss with details about this claimed variation and the actual status of the variation of alpha from quasar absorption spectral data. On the other hand, data from the cosmic microwave background can allow us to set constraints on the variation of the fine structure constant and the electron mass in the early universe. Finally, also constraints on H, I will show how constraints on H0 can allow us also to put bounds on the possible variation of the fine structure constant. The second part of the talk will be devoted to the theoretical research. Among this research, there are two big of theories. The first of them, as I told you before, are theories that attempt to unify the four fundamental interactions, and in this sense, I will first describe a phenomenological model that arrives from this kind of theories, and I will describe a prediction of a related variation of the fine structure constant, and mu, I will use one of the constant I will consider is mu, the proton to electron mass, because a lot of experiments are just sensible to this quantity. Then I will describe the predictions of another unifying model, that is string theory. I will show the low energy limit of string theory and a particular model of dilatons. And finally, I will introduce to you a different kind of model, namely a phenomenological model proposed by Bekenstein and later improved by Sandy, Barrow, and Mageijo for the variation on alpha, and there is also another model for the variation of the electron mass. I will also show how the local and astronomical bounds can put constraints on the free parameter of this. So, as I told you before, I will begin with the local data, and one of the most stringent bounds on a variation of fundamental constants follows from the analysis of isotope ratios of Seminário in the natural uranium fission reactor that operated about 1,800 million years ago in the present site of the Oklo mine in Oklo, Gabon, Africa. From nuclear and chemical data, the operating conditions of this reactor could be reconstructed, and the thermal neutron capture cross sections could be calculated. But first, let me tell you how the people concluded that this phenomena of a natural nuclear reactor took place such a long time ago in a place where now there is an ore mine. So the proof of the existence of the chain reaction are the following. First, the quotients of uranium-235 to uranium-238 find in the zone of the reactor were far less than the terrestrial standards. On the other hand, the observed isotopic distribution is consistent with the effect of a strong neutron flux. And finally, neutron absorbers such as samarium and gadolinium were found in very small quantities in the central regions of the reactor. So all these hints led to the scientists to establish that this phenomena happened this time ago. And I'm putting the equality with redshift because then we want to compare with other astronomical data, so redshift I think is something important to compare the scale of time, the time scale. Okay, in order to put bounds on the variation of fundamental constant, the reaction that is interesting for us is the reaction where samarium 149 captures a neutron and converts in samarium 150. The scattering cross-section of this reaction can be written as follows. This reaction could be calculated from, as I told you before, from the nuclear and geochemical data. People could reconstruct this number, and they also could reconstruct what is more important, the resonance energy, which is sensible to variation of fundamental constants. So from this data, the resonant energy at the Oklo time could be measured, and this energy in comparison with the energy of the same reaction measured today in the laboratory has these bounds. And we can translate this difference in a combined bound of the fine structure constant and geofermi, which I remind you is related to the gauge coupling constant of the weak interaction. So as you can see, the bound on delta alpha over alpha is of order 10 to the minus 8 and is one of the most stringent bounds in the present on the fine structure constant, on the possible variation of the fine structure constant. The most stringent bound, and I will emphasize this a lot, just apologize for my insistence, the most stringent bounds on variation of fundamental constant follow from the comparison of atomic clocks with different atomic number. This is a present day variation of the fundamental constant. So this is a variation that is measured over maybe 1 year, 2 years, or 5 years. But remember, the Oklo bound is 1,800 millions, happened 1,800 millions years ago. The age of the universe is about 1,400 millions years ago. So measuring a variation during 5 years is a present day variation. It's a variation that happens during 5 years, but it's the same to say that it happens in this moment. Okay, so this bound follows from the fact that the characteristic frequency of the clocks corresponds to the frequency of some atomic transitions. So, for example, the dependence of an hyperfine transition frequency with the fundamental constant can be expressed as follows, when here you have the relativistic contribution to energy, and this is interesting because this relativistic contribution goes as the fine structure constant times the atomic number. So it's easy to infer that if you compare two hyperfine frequencies of two different atoms, you will find bounds on the fine structure constant and also on the gyromagnetic factor of both atoms. On the other hand, if you have an optical transition frequency, the dependence of alpha is different. It's only with alpha. It does not depend with the atomic number. But if, for example, if you compare an hyperfine transition frequency with an optical transition frequency, you can get combined bounds on the fine structure constant, the proton to electron mass, and the gyromagnetic factor of the hyperfine transition. Just to summarize the idea that I'm trying to describe you, let me say the following. If you compare two hyperfine transitions frequency, you get bounds on the quotient of the gyromagnetic factors of the atoms times alpha to some power. While if you compare two optical transitions frequency, you will get bounds on only of alpha to some power, dependent, the power will depend on which atoms you are comparing. And finally, if you compare the optical transition frequency with an hyperfine transition frequency, you will get bounds on the gyromagnetic factor of the hyperfine transition, the proton to electron mass, and alpha to some power. So, in this table, I am just summarizing the different measurements, the different experiments that were performed by different people, and this is just to show you that you get for example, these are two optical transitions, these are two hyperfine transitions, and this last is the comparison of the hyperfine transition of cesium with optical transitions. So in this case, you get a combined bound on the gyromagnetic factor of cesium, the proton to electron mass, and alpha to some power depending on the atoms that you are comparing. One of the most stringent measurements is the ones of Rosenbaum et al. And you just keep it in mind, because at the end, when we are going to compare the theoretical prediction with the data, we will use just the measurement of Rosenbaum et al. So if you combine the data from this table, you obtain the following bounds on the variation of alpha and mu. Mu, remember, is the proton to electron mass in units of years to the -1. You see that this is a very, very stringent bound. If you think that you have that dot alpha is delta alpha over delta t, and this is in units of years, you divide by 1 year, so you get a bound on delta alpha over alpha of order 10 to the -16 or 10 to the -17, which is much more stringent than the Oklo bound that was about 10 to the -8, which is also very stringent. Okay. Now I pass to the astronomical methods. Quasar absorption systems are ideal laboratories in which to search for the variation of constant, because, as you know, if you know the laboratory wavelength of some transition, the observed wavelength at some astrophysical system will be amplified by redshift. So the physics you are really measuring, it's not the physics from the quasar, but it's the physics from the absorption clouds, because the light starts from the quasar, is observed here on Earth, but in the middle it is absorbed by these absorption clouds that are in the way of the light between the quasar and the observer. So the physics that you're really measuring is not the physics of the quasar, but are the different transitions that happen in the absorption clouds. There are different methods to put bounds or detect variation of the fundamental constant. Some of them are based in comparison between the wavelength measured at astrophysical system with the wavelength measured in the laboratory, and the others are just comparisons of redshift measured with different methods. For example, the redshift measured with an optical from an optical transition to a redshift measured, for example, from a radio transition. In some sense, the reasoning is very similar on what happens with the atomic clock method. You are just comparing different transitions which have different sensitivities to the fundamental constant in order to put bounds on the possible variation of them. So, the first method that was developed is the double alkali method that employs the doublets of alkali atoms such as silicium, carbon, magnesium. So this method compares the doublets obtained in astrophysical system with the doublets, with the same doublets measured here in the Earth. And from this comparison, they obtain, since the width of the doublet is proportional to alpha to the square, if you compare the doublet measured in the astrophysical system with the same doublet measured here in the Earth, you get bounds on the possible variation of alpha, and these are the data obtained in the literature, and you can see that the bounds are not very stringent. They are of order of 10 to the minus 4. In order to improve this method, the many multiplet method was developed by the group of Webb et al. This method allows us to obtain more stringent bounds on the variation of the fine structure constant, and it is based on the energy equation. And it is based in the fact that the energy equation for a transition to the fundamental level can be expressed as follows. And here you see again, as in the atomic clocks, that this energy depends on the possible variation of alpha, but also of the atomic number of the transition. So again, comparing transitions of atoms of different atomic number, you will be able to get stringent constraint on the possible variation of the fine structure constant. So the method consists in adjusting point profile, as it is usually done in astronomy, of several absorption lines, including, besides the usual field parameters, column density, Doppler width, and redshift, a possible variation of the fine structure constant. So this method was first used by Webb et al. With the Keck telescope, and in 1998 they claimed for a variation of the fine structure constant of an order of 10 to the minus 5. However, a year ago, another group took data with the VLT telescope and found no variation. So the group of Webb et al. Decided also to take data from the Webb telescope, but they didn't ask for observing time. They just took archival data from VLT and reanalyzed this data and obtained that the variation of alpha was positive. Remember that the variation that they obtained with the Keck telescope was negative. So they obtained a negative variation for the Keck telescope, a positive variation for the VLT telescope, and so they proposed that the fine structure constant should have a dipole-like variation with the dipole centered here in the Earth, which is very difficult to believe that from all the universe the fine structure constant is going to vary with a direction that is placed here in the Earth. However, I have to stress, it is important to stress that these measurements that they took from VLT were not measurements that were proposed to measure alpha variation or any fundamental constant variation, and in this sense they had several issues with wavelength calibration that is very important in order to test such kind of variation. It was because of this that several observers decided to perform new measurements both with Keck and VLT telescopes, and the plot in the left are the 293 measurements of Webb et al. Which give negative variation of alpha for the Keck data and positive variation for the VLT data. While the plot in the right shows the results of new 21 dedicated measurements at redshift between 1 and 2.4, and I remind you, these measurements are also done, the half with VLT, the half with Keck, but they are specifically done for measuring the possible variation of fundamental constant. And you can see that in the results, are very different, because the results of the weighted mean of the Webb et al. Data are consistent with a variation of alpha at more than 4 sigma, while these 21 dedicated measurements are not consistent with any variation at all. Finally, let me also say that key improvements in the data acquisition of these 21 dedicated measurements include obtaining calibration lamp exposures attached to science exposure and observing bright asteroids at twilight to monitor the radial velocity occurrence of UVs, which is the spectrograph of DLT, and the optical alignments. So, the actual status of the possible variation of the fine structure constant is that there is no variation, nor time variation, nor dipole variation. Okay, now let me change the subject a little and go to a different astronomical method that relies in the comparison of molecular and laboratory spectra. This method is based in the fact that the wavelength of a molecular line can be expressed as follows. This is the wavelength measured at the laboratory. This is the measured at an astrophysical system. And this is the possible variation of the proton to electron mass. So comparing transitions of different molecules will allow us to set constraints on the possible variation of the proton to electron mass. And the plot shows all the measurements available today as a function of redshift, and you can see that most of them are consistent with no variation of the proton to electron mass. This table shows just all the measurements that I showed before in the plot, but I put this just to show that the different transitions that are used in each measurement. In order that you see that we are not measuring only one transition, even though most of the transition came from hydrogen, but not all of them are from hydrogen. So these different data follow from different transitions, from different molecular transitions, and their comparison with the same transitions in the laboratory. Okay, the next methods I am going to describe are methods that compare redshift taken from some transition with redshift taken from another transition, and the transitions will have different dependence on the fundamental constant. So, for example, we know that the ratio of the hydrogen 21 centimeters transition to a metal optical transition can be written as follows. In such way, if you compare the redshift obtained from the optical transition and the redshift obtained from the 21 centimeter transition, you can find combined bounds on alpha, the proton to electron mass, and the shear magnetic factor of the proton. A very similar method in his philosophy is the one that compares the ratio, compares the redshift of the 21 centimeter transition to a molecular transition frequency. And in this case, you can place bound on the combined variation of the fine structure constant and the shear magnetic factor of atoms. So, with the same philosophy, if you compare the redshift taken from the rotational lines of carbon with the redshift taken from the fine structure lines of neutral or ionized carbon, you can find a combined bound on the fine structure constant and the proton to electron mass. However, the last three methods that I have described have a problem, namely that sometimes it is not easy to know if the transitions that you are comparing really happen in the same absorption cloud. So, from my point of view, these two methods and this one are the worst method that we can use to measure possible variation of fundamental constants. For this, the satellite conjugate method is a method that improves on this. This is because we call satellite lines, satellite conjugate lines that arise from the same absorption cloud, but one in emission and the other, and the same arise from the same molecular cloud and the same transition, but one line is in emission and the other line is in absorption. So if you compare the redshift obtained from the emission lines and the redshift obtained from the absorption lines, you get a combined bound on the gyromagnetic factor of the proton to electron mass, and the fine structure constant. And with these methods, you are really sure that you are measuring the possible variation in the same absorption cloud.
Susana?
Yes.
From the theoretical point of view, you should expect direct relation between the variation of alpha and the variation of V, or not? Or it's two independent?
This depends on the theory. The best motivated theories are the theories that arise from unifying schemes. So in these theories, all constants should vary at the same time. So there is a theoretical motivation for this joint variation.
Okay.
However, most of the theories that really predict such kinds of variation are really ruled out. So it is not easy to find an exact expression for the predictions of some variation. But the combined variation as is theoretical motivated. Okay. Good. In this table, I am showing. In this plot, I am showing the possible variation of Q, where Q are all the quantities are named before. F, Q refer to X, Y, F, and G. Okay, all are named as Q. These are the possible variation of all the different quantities with redshift, and you can see also that most of them are consistent with no variation of the fundamental constant.
This is multiplied by 10 to minus 6, right?
Yes.
Okay.
Yes. And I have to ask you then to keep in mind that because later I will be comparing bounds from different data, so I will call this data, these 21 dedicated measurements, I will call them table 1. These ones I will call them the web data. The new data, I will call them table 2. I will remind you, but just to define them now. And this last data, I will call them table 3. And then we will see what happens if we combine all these measurements, if there is consistency about among the different data sets or not. Okay, here is the table. So you see, remember, table 3 are the bounds on the different quantities named Q, and table 2 refers to the bounds on the proton to electron mass. Table 1 refers to the 21 dedicated measurements for delta alpha over alpha, and W refers to the Webb et al. Data. And here are the results of considering the different data sets and the different quantities. And the last table shows the reduced chi-square value. And the first thing one notices are the large values of chi-square on this table. So one guess is that the systematic errors are underestimated, but if they are not, one can say that there is not much consistency about the different data regarding bounds on the fundamental constants. Last but not least, I also would like to mention the possible dipole variation of alpha, because it was widely discussed in the literature, even though it is now ruled out. But I would like to explain why it is now ruled out. So, the proposal was to postulate that the possible variation of alpha is not a variation with time, but is a variation with space, and the expression is here, where the phi I and theta I are the declinations and right ascension of each measurement, and theta 0 and phi 0 are those of the dipole governing the variation of alpha. So, you can see that if you consider only the data of Webb et al., you find evidence for a dipole, you find statistical evidence for a dipole preference at more than 4 sigma. And you also find a preferred direction in ascension and declination. On the other hand, if you only consider the 21 dedicated measurements, you find there is no evidence for a dipole-like variation. And finally, if you combine all data, you find that the statistical preference for a dipole-like variations shrinks to 2.3 sigma. So 2.3 sigma, in my opinion, is not very relevant. And also you can see that the directions of the dipole changes if you add more data. So because of this, poor evidence for a dipole variation with alpha is that I say to you today that the evidence for a dipole-like variation of the fine structure constant is now ruled out. Okay. Now I will change a little bit the subject and show how data from the cosmic microwave background allow us to put constraints on the possible variation of the fine structure and the electron mass in the early universe. You know that after the Big Bang, the universe can be regarded as a hot, dense plasma full of protons, electrons, and photons. This plasma was effectively opaque to electromagnetic radiation, and as the universe expanded, it also cools, and eventually it came to a time where the formation of neutral hydrogen was favored. This time is technically called recombination. After the recombination, the photons are allowed to travel freely to the universe and constitute what we call today the cosmic microwave background. As you know, the cosmic microwave background is one of the best tools we have today to study the physics of the early universe and also to study the content of matter of energy of the universe. There are several surveys dedicated to measure such radiation, and what you really measure are maps from are temperature and polarization maps. But the observables that you compare to the theoretical predictions are the autocorrelation spectra of temperature and for example, the cross-correlation spectra between temperature and the E mode of polarization. These plots shows the data acquired by the Planck, and the line in blue shows the best fit of the theoretical prediction. And I forgot to say that I think you all know that this is, the measurements from the cosmic microwave background are performed both by Earth-based telescope and also by space-based telescopes such as WMAP and Planck. Okay, but what the interest for us in this talk is how can the measurements of the cosmic microwave background allow us to put constraint on the possible variation of the fine structure constant and the electron mass in the early universe. And for this, it is important to note that the most important effects that are affected by the fine structure constant and the electron mass in the early universe are the following. First, a change, the Thomson scattering cross-section depends both on the fine structure constant and the electron mass. And second, the ionization fractions can be expressed in function of the electron mass and the hydrogen binding energy, which depends on alpha and the electron mass. So, in these plots, I am showing on the right the red lines is the prediction of the standard model, a standard model that was many years ago, because this is old, I am sorry. The first line, the red line shows the prediction with no variation of alpha, while the green and blue lines show variations of order 5%. And you can see that there is an important effect if the value of the fundamental constant vary at such early times. This plot shows the same variation, but for the temperature, for the cross correlation between temperature and the E mode. The plots on the left show the same idea, but this time the constant that is varying is the electron mass. You can see that the effect is not so important, but it affects the power spectra of both temperature and the cross correlation between temporal and polarization. So if one includes the fine structure constant and or the electron mass as an extra parameter when you fit the data from the cosmic microwave background, you can obtain bounds on the possible variation of this constant at the time of the formation of neutral hydrogen. So the results, this was performed by the Planck collaboration, and the results, assuming independent variation for alpha and electron mass, are shown here. They are order of 3 to the minus 3, considering only CMB data, and in the case of the electron mass, they considered also data from baryon acoustic oscillation, but the order of magnitude of the bounds are also of order 10 to the minus 3, while if the joint variation of both constants is assumed, you obtain these bounds, which are also of order 10 to the minus 3. So the bounds from the cosmic microwave background are perhaps not as stringent as other bounds, but are important because they allow us to place bounds on alpha at very early times in the history of the universe. Okay, so I will move on telling you how data, how bounds, how measurements on H0 allow us to also to play constraints on the variation of alpha. I thought that this seminar that people outside the cosmology group were going to be here, so for this I introduced something that I think probably you all know, that the homogeneous and isotropic universe is well described by the Friedmann-Robertson-Walker metric, and the relation of the scale factor and redshift is the following. And if you assume a spatially flat Friedmann-Robertson-Walker metric, you obtain this expression for the Friedmann equation. Okay. Furthermore, the Hubble parameter, depends on the differential age of the function of redshift. So if you have a determination of the set of dt, it is like a measurement of H0, and this is performed like that. Redshift can be measured using spectroscopy and comparing with laboratory spectra as usual, and the age of the star or galaxy can be determined using photometry and also a galactic or a stellar models. So what has this to do with the possible variation of alpha is the question that you probably are making to yourself. So the Friedmann equation in the case of a varying alpha will be modified as follows. With this function will depend on the specific model you are postulating. So the bounds I described before were all model independent. Really, they were not exactly model independent because, for example, for the Oklo bound, you are putting some nuclear models. But the other bounds, the ones coming from atomic clocks and from the quasar, the bounds that you take from the data are model independent. You can obtain a model independent bound on delta alpha over alpha, and then compare this bound with the theoretical expression. This is not the same for this case. In the case of H0, you have this theoretical expression for H0, and according to your theoretical model, you will put a different function here and then obtain a bound on delta alpha over alpha. However, I am mentioning this because the fits I will mention at the end of the talk, where I will compare the theoretical prediction with the bounds from different experiments, I took them, these are not the fits that I've performed by myself, I took them from a report of Carlos Martins. They take into account these bounds, and for this it was important to describe the origin of these bounds. So okay, now in this table I am just summarizing all what I talked about, all the bounds on delta alpha over alpha. The atomic clocks, I already mentioned that it is the more stringent bound that we have today, followed by the Okla bound. About the quasar data I have talked a lot, but I have not talked about bounds coming from supernovae, galaxy cluster or white dwarf, or even primordial nucleus, synthesis, and the reason for this is that it would take maybe an entire course to talk about them. And as you can see, the order of magnitudes of these bounds are lower than the other ones. If you want, at the end of the talk, I can describe you with some detail how the bounds of nucleosynthesis arrive. Let me just tell you that at the present, you can measure the abundances of the elements that were formed during the primordial nucleosynthesis, which are deuterium, helium, and lithium. And for these abundances, you also have a theoretical predictions, which depends on the fundamental constant, mainly alpha, G of Fermi, and also the scale energy of QCD, lambda QCD, which I mentioned in the introduction and then came back again. Well, now it came back. So the abundances of the primordial elements such as deuterium, helium, and lithium depend on these three constants, and from the comparison of the present abundances with this theoretical expression, you can obtain bounds of order 10 to the minus 2 on the variation of this constant at these very, very early times of the universe. So here again, you can see that the interesting thing about this subject is that you have bounds coming from different times in the history of the universe. And this is why I found this subject very interesting always. Here I am also summarizing the bounds you obtain, again from atomic clocks, quasars, CMB, which I also have described before, for the possible variation of the electron mass, and also I added the white dwarfs and nucleosynthesis bound. As I told you before, there are two big groups that predict variation of fundamental constants. One of them arises from theories that attempt to unify the four fundamental interactions, such as string theories, Kaluza-Clay theories, or maybe related brane theories. And the other big group is the phenomenological model, where the model is just constructed to model the variation of a fundamental constant. That could be alpha, the electron mass, or the varying speed of light. So here I will just describe to you a quite generic parametrization of joint variation that has been developed by Koch et al. Well, they relate. So they considered a class of unification models. They took some similarities among them, and they obtained these expressions and a relationship between the possible variation of the electron mass and the variation of spin structure constant, and the same for the possible variation of the proton mass. And this R and S will depend on the details of the phenomenological model. Again, if you want, at the end of the talk, I can describe some detail of that. But if you combine these two equations, you obtain this relationship between the proton to electron mass, the possible variation of the proton to electron mass, and the possible variation of the fine structure constant. So, taking all the atomic clock data and making a fit, you can find these confident contours in the RS plane, where the difference between these plots are what are the details of the phenomenological model that you are assuming. You can see that this is very degenerated because, and this is the reason for this is that you're only using atomic clocks. If you add quasar data to this statistical analysis, you will see that the contours will close. But this has not been performed yet. Okay, I will pass this model because I want to get to the end without rushing, and I will present you as I told you before, a phenomenological model for the variation of alpha. So this is not a model which attempts to unify the four fundamental interactions. This is a model just built for the variation of alpha that was proposed first by Bekenstein and later on improved by Sandwich, Barrow, and Mageijo. Here I wrote the action of the model, and in magenta I put the extra terms that are added for the variation of alpha. So as you can see, this is a usual particle physics model with a scalar field that is added, and this scalar field is coupled to electromagnetism in this way. So for the scalar field, we get this equation. This is the equation of motion of the scalar field. You can see that the dynamics of this field, the source of the dynamics, is the coupling of this dilaton, this scalar field to matter, and the variation of this field is related to the variation of alpha. On the other hand, the Friedman equation will also be modified in this way. An extra term will be added for the energy density of the scalar field, but this will be very low. The intensity of this term is not very important. Which is more important is the coupling of the scalar field to the matter sector and to the radiation sector. So in this way, and you can write the energy density as a free parameter times the derivative of the field to the square. So the free parameters of this model will be the intensity of the energy of the scalar field and the coupling of the scalar field to matter. So roughly speaking, in the matter era, the expression, the dependence of the possible variation of the fine structure constant is a logarithmic dependence with redshift. So, as I told you before, I used the work of Carlos Martins, a report of Carlos Martin, where he considered the Union 2.1 dataset of 580 type 1a supernovae, a compilation of 38 Hubble parameter measurements. This is the one I referred when I told you the constraint coming from H0. All the astrophysical measurements, the quasar data from Webb et al., as well as the 21 dedicated measurements listed in Table 1, the atomic clock constraint on alpha, only the one by Rosenblatt et al., who is the more stringent one, and the O-clock constraint. Carlos Martin, they decided to fix omega to 1 and put the omega m and no, this is not good. I'm sorry. The only free parameter in this fit is the coupling of the scalar field to matter, and so using all this data, comparing it with the expression from this model, they obtain these bounds on the coupling of the scalar field to matter, which you can see is very little. This is consistent with no variation, and the reason for this is obviously that all the data indicate that there is no variation of the fine structure constant, and therefore the coupling of the scalar field, which should be responsible for alpha variation to matter, should also be very small. Finally, it is important to say that every time you have a theory where the fundamental constant vary, you also have a violation of the equivalent principle. So the bounds on the variation of alpha can be translated on a bound on the U-push parameter, which measures the differential acceleration of two bodies of different composition falling to the Earth. And so this bound can be put, so they are experimental bounds on this quantity that are of order 10 to the minus 13, the present bounds. But if you consider the relationship between the U-push parameter and the possible variation of alpha, you get, from this fit, you get a more stringent bound. Okay, in the last minute I will present you the Bekenstein-Barrow-Magejo model, but this is a model that models only the variation of the electron mass. So, in this model, again, you have the action where you add a scalar field and an interaction between this scalar field and matter. In this sense, it is different from the one from the model. In the model where the fine structure constant was varying, we had an interaction of the scalar field with the electromagnetic sector. In this case, you only have an interaction of the matter sector with the scalar field, and as in the model of alpha, the variation of the scalar field is related to the variation of the electron mass. So again, the Friedman equation is modified as follows. Here we only add the term of the energy density of the field responsible for the variation of the electron mass, and the equation of evolution for this field is expressed here. And so here we have only one free parameter, that is omega, and in the matter era we also obtain a logarithmic type dependence with redshift. So finally, so Martins performed another feat in order to test the expression of this model for the variation of the electron mass with, again, the data from one type A supernova, the compilation of the 38 Hubble parameter measurements, the measurements listed in table 2. Remember, there were the bounds from the quasar absorption systems for delta mu over mu, the atomic clock constrained by Rosenblatt et al. The Oklo data, they don't consider them because they don't put bounds on the Oklo bound doesn't put bounds on the possible variation of the electron mass. And finally, so he obtains he defines this zeta mu, which is related to the free parameter of the theory that was omega. So he obtains bounds again for zeta mu that is related to omega, which is the coupling, which is the density, the energy density of this scalar field responsible for the variation of alpha, and is also in the sector of coupling of the field with matter. So these are the bounds that are obtained for this parameter. So as a conclusion of all the things I have shown, the most important message to take home is that there is no present evidence for time or spatial variation of the fundamental constant. The most stringent limits are provided by the atomic clock experiments, that they are present limits on the variation of the fundamental constant. So if the fundamental constant are varying in time or space, they are sure not varying today. Maybe they have had different values over cosmological times, but in the last 100 years, the charge and mass of the electron are the same. On the other hand, combining the limits from atomic clocks with the astronomical bounds from quasars, bounds on grand unification theory can be obtained, and experimental or observational bounds can be used to place limit on the free parameters of the theories that predict the variation of fundamental constant, and in this way test the validity of such theories. And finally, last but not least, some of the theories that predict variation of fundamental constant are also provide an explanation for the late time acceleration of the universe. Okay, thank you very much.